Welcome to the presentation of the paper Bitcoin-compatible virtual channels. My name is Andreas Erwig, and this is joint work with Lukas, Osan, Sebastian, Christina, Matteo, Pedro, and Siavash, and this will be a joint talk together with Lukas. In this work, we achieve an efficient, privacy-preserving, cheap, and interoperable payment solution for cryptocurrencies. Now, to start off with some motivation, most cryptocurrencies nowadays use as an underlying building block the blockchain, which is a data structure that collects data in blocks and then cryptographically connects these blocks to achieve data integrity. Now, in a cryptocurrency network, if we have two parties, Alice and Bob, and Alice wants to make a payment to Bob, she sends a transaction to the underlying network, and this network will then eventually include the transaction into the blockchain. And once this has happened, Bob can see the transaction in the blockchain, and he knows that Alice made a payment to him. The blockchain has two characteristics. First, it has a fixed block size. That means there can be only so much data in one block. And second, there's an average block time. That means there can be only so many new blocks in a certain time period. From this results that cryptocurrencies have a limited transaction throughput and high transaction fees, which is known as the blockchain scalability problem. And one of the most promising proposals to solve this problem are so-called off-chain protocols, which allow to run applications on the blockchain while only having minimal interaction with the blockchain itself. For the application of sending payments, the most promising off-chain solution are so-called payment channels, which allow two parties, Alice and Bob, to make payments without involving the blockchain at all. Ledger payment channels consist of three procedures: create, update, and close, where if Alice and Bob want to create a channel, they lock a certain amount of coins on the blockchain. This process is also called as funding the channel on the blockchain. And once this is done, the channel is considered to be open with an initial state as 0, where Alice, for example, owns 10 coins and Bob owns 10 coins. Now, Alice and Bob can make off-chain payments to each other by updating this channel to a new state as 1, where Alice, for example, now owns 15 coins and Bob owns 5 coins. And this can happen multiple times until some end state as n, where Alice owns, for example, 18 coins and Bob owns 2 coins. Now, in order to close the channel and actually receive these coins on the blockchain, Alice and Bob send the latest state as n to the blockchain, which will then distribute the coins according to the latest state. This solution is nice because it allows for off-chain updates, but it still requires on-chain creation and closure, which is suboptimal as off-chain protocols aim to reduce the amount of interaction with the blockchain. In order to improve this solution, the notion of payment channel networks has been introduced, where we have a network of payment channels. Between Alice, Ingrid, and Bob, we have channels alpha and beta. And now if Alice wants to make a payment to Bob, she can send a payment to Ingrid, and then Ingrid can forward that payment to Bob. This solution is nice because it works entirely off-chain, but Ingrid must be active in each payment as she has to route the payment. And because of this, there's also no privacy because Ingrid learns the content and the amount of transactions between Alice and Bob. And also because Ingrid must be active all the time, she requires a fee for each payment. Now, finally, there has been the proposal of virtual channels, where we have again Alice, Ingrid, and Bob, and channels alpha and beta. But this time, Alice and Bob use the channels alpha and beta to create a new channel, gamma, the so-called virtual channel, that consists exactly of the same procedures as ledger channels, so create, update, and close, but with the difference that even create and close can be executed off-chain. So this protocol is entirely off-chain. Ingrid is involved only in the creation and closure, so she's not involved in each single payment, and therefore we get some privacy-preserving guarantees. But the problem is that existing solutions so far always required smart contracts, which are Turing-complete programs that can be executed on the blockchain. Now, this is where our contribution comes into play. We provide the first construction of a virtual channel for UTXO-based blockchains, and in particular for blockchains with only limited scripting functionality that cannot execute powerful smart contracts. We give a formalization of the security properties of virtual channels in the UC framework. We give a UC security proof, and we provide an implementation and evaluation of our results. As an outline of this talk, I gave some motivation. Now I will give an overview of our construction. And then I will briefly talk about the security properties and comparison to previous solutions. And then Lukas will talk about the performance and evaluation. So on a high level, how can we build a virtual channel based on channels alpha and beta? So if we have the setup we have parties Alice, Ingrid, and Bob, and channels alpha and beta with states S alpha I and S beta I. In order to create a virtual channel, the parties have to update the ledger payment channels alpha and beta to a new state that we call as open, where the balances of the parties get reduced by C coins, and instead these coins get assigned to a new channel gamma. Once this is done, the channel gamma is considered to be open with an initial state as gamma 0, where Alice owns C coins, Bob owns C coins, and Ingrid owns no coins in the channel, but she has a collateral of 2 C coins. Now, this virtual channel can be updated in exactly the same way as a ledger channel. So Alice and Bob can simply update the state of this channel among each other multiple times until they reach an end state as gamma n, where Alice, for example, owns all the coins in the channel, Bob owns no coins, and Ingrid still has a collateral. Now, in order to close the channel and actually receive the coins from the virtual channel, the parties have to again update the ledger channels alpha and beta to a new state as close, which now reflects the latest state of the virtual channel. So here we can see Alice has now C coins more than before the virtual channel. Ingrid has C coins less in alpha, but she has C coins more in beta, and Bob has C coins less in beta than before the virtual channel. So this is exactly the coin distribution that we require after the virtual channel. From this high-level overview, we can already see that virtual channels are fairly similar to ledger channels, and in fact, virtual channels are exactly like ledger channels, with the only difference being that virtual channels are not directly funded on the blockchain. Now, what are some challenges that arise when we want to build virtual channels? The first challenge is that any party of Alice, Ingrid, and Bob can prevent the closure of the virtual channel. So in our example, for example, Bob lost all his coins in the virtual channel, so he has no incentive to actually close the virtual channel correctly. So he can, for example, just refuse to update the channel beta correctly. In that scenario, Alice and Ingrid need to have a way to publish the latest state of the virtual channel to the blockchain so that they can still receive their coins. This by itself is quite challenging because the blockchain doesn't even know that the virtual channel gamma exists. Another challenge is that 2 corrupted parties that collude can maliciously update one of the ledger channels and thereby revert the state of the virtual channel. So for example, if Ingrid and Bob are malicious and they simply update their ledger channel beta to a new state where again Ingrid has all her coins and Bob has all his coins from before the virtual channel, then Alice has no way of receiving actually her 2C coins from the virtual channel. So we need a way that parties can still receive their coins even if malicious parties try to prevent this. How do we solve these challenges? The first challenge that any party can prevent, for example, the closure of the virtual channel, we solve by introducing a procedure offload, which essentially publishes the opening states of the ledger channels to the blockchain. Now, this is the first time that the blockchain actually learns about the virtual channel gamma because these states include 2C coins that are assigned to gamma. In fact, this actually funds the virtual channel on the blockchain. And since we said that virtual channels are just ledger channels that are not funded on the blockchain, this process will actually transform a virtual channel into a ledger channel. The second challenge that 2 malicious parties can update one of the ledger channels, we address by introducing a punishment procedure. This procedure is executed if the offload procedure fails. So for example, because of the malicious behavior of the 2 parties. And then the punishment procedure allows to punish the malicious parties such that they lose all the coins in their ledger channel, whereas the honest party gets financially compensated. I will now briefly talk about security properties and some comparison to previous solutions. So informally, what we require as security properties is that Ingrid does not have to be an intermediary indefinitely. So for example, assume that Alice and Bob simply never close their virtual channel, then Ingrid would be stuck as the intermediary in the virtual channel. So she has to have the guarantee that eventually she can lose the role as the intermediary. Second, we require balance security for Ingrid. That means that if Ingrid is honest, she will never lose any coins. So if she loses some coins in one of the ledger channels, she will gain the same amount of coins in the other ledger channel. And finally, because virtual channels are just ledger channels that are not funded on the blockchain, virtual channels inherit all the security properties of ledger channels. For the comparison to previous solutions, I mentioned before already that previous solutions rely on smart contract support because the underlying blockchain needs to be able to interpret arbitrary messages. And because of this smart contract support, previous solutions do not require a punishment procedure because the smart contracts can guarantee that the offload procedure actually succeeds. Now, our solution does not require powerful smart contracts, but it can work only with limited scripting language that in fact only supports time lock functionality and a signature verification. This scripting functionality is supported by virtually any blockchain, and therefore we have a high compatibility with a lot of cryptocurrencies. On the other hand, we need the punishment procedure in case of malicious behavior, like I explained before. I will now turn it to Lucas for the discussion of our performance and evaluation.
Let me talk about the evaluation of the paper. We implemented a proof of concept that creates the raw Bitcoin transactions needed for the construction and deployed them on the Bitcoin testnet in order to showcase the compatibility with the current system. Finally, we measured the transaction overhead in terms of size, numbers of transactions, and on-chain fees if there are any. Here are the results. I will not go over them in detail, but instead highlight some key points. For instance, for these three operations, create, update, and close, there are no on-chain fees. Instead, for these two other cases, the offload and punish, we have some on-chain fees. These are the cases that happen only in the dispute or if someone wants to offload the channel. And we point out that, for instance, for the punish, this is roughly the same cost as closing a payment channel. Now, if we compare this with the current state of the art, so we say we want to measure the communication overhead of routing payments through virtual channels with the payment, with routing payment to the payment channel network. Now, what happens in a payment channel network in a payment? Let's say Alice wants to pay to Bob via Ingrid. They coordinate the two underlying channels in the following way. First, they update both of them and lock the amount cash. And once this has been done, they update the channels once more in order to unlock the cache again. In the virtual channel, what we do instead is Alice and Bob create the virtual channel gamma. And when this is done, they can perform arbitrarily many payments and finally close the channel again. Now, in terms of communication overhead, let's say we want to perform n payments. In the payment channel network case, this means 3026 bytes per payment or n transactions per payment. In the virtual channel case, this is 3524 bytes plus 695 times n. Again, n is the number of payments, or it is 9 plus 2 times n transactions. So note that this constant part on the left is a one-time cost. This is the cost for opening and closing the virtual channels, while the small part on the right is actually the one that we need to pay for every payment. And indeed, if we look on the graph on the right, we can actually see that the virtual channels are already more efficient for a number of payments that is greater than one. Now let's talk a bit about fees. In payment channel networks, such as, for instance, in the Lightning Network, which is one of the more prominent current solutions, the following fee is charged. So let's say one payment is routed through Ingrid of amount cash. She charges a base fee plus a fee rate times the amount. So this base fee is a fixed amount. We can say that it's charged for Ingrid being online, and then there's a fee rate that's proportional, and this is charged because Ingrid needs to lock up some money. Now, if we have n payments, and these payments sum up to a total amount of cash, Ingrid will instead charge n times the base fee, plus again the fee rate times the total amount. So Ingrid charges for every payment. Now, instead in the virtual channel case, Ingrid will only charge for the opening of a virtual channel. So we can say again, this might be this base fee plus the fee rate times the total capacity, but then the subsequent payments are for free actually, no fee is charged for them. So to sum up, we presented in the paper the virtual channel constructions in the UTXO model with limited scripting capabilities. We formalized this in the universal composability model and gave a security proof, and we did an evaluation and compared this with payment channel networks. For future work, one could think about constructing recursive virtual channels. What this means is the virtual channels are not constructed on top of two payment channels, but instead on top of other virtual channels. And the other thing would be to add a support for users going offline, which is also known as a watchtower support. Thank you for your attention.